With computer audio. Hello, this is going to be the last section for chapter number 2. Unit number 4, atoms, molecules, moles, and Avogadro number. Going to share the screen with you, and here it goes. So we are at the end of the particular chapter, and let's go quickly and review this particular chapter and what it contains. At the end of this particular chapter unit, you will still find study questions. I'm still deciding what to do with the study questions, whether I should give it to you all as assignments and then score it, or just leave it as a review question for you, for the students. So I'll let you know later on, because if I have to give it as assignment, then you all will need to copy those questions onto a Word document and solve it and then submit it for grading for all the chapters that we are going to be doing. So first, atoms, molecules, and the mole. We have to understand the mole concept and the molar mass and their application. Use the molar mass of an element and Avogadro's number in calculations. Calculate the molar mass of a compound from its formula and the table of atomic weights. Calculate the amount, number of moles of a compound represented by a given mass and vice versa. Use Avogadro's number to calculate the number of atoms or ions in a compound. The chemical analysis. And that's the last topic for chapter number 2. Determining the compound formula. Express the composition of a compound first in terms of percent composition. Once you get the percentage composition, then you can determine the empirical and molecular formula of a compound using percentage composition or other experimental data that is provided. So how we do that, as we go along with the various slides, I'm going to explain it to you. First, the mole. The mole is a counting unit for chemistry and chemists. It can represent atoms, molecules, ions, and is designated as 1 mole of any particle consists of 6.022 times 10 raised to 23 units. This is a very, very large number when you compare to other units that you have studied. For example, eggs is sold by a dozen. Paper is sold by a ream, which contains 500 sheets. But atoms, molecules, and ions are talked about in terms of mole, which represents 6.022 times 10 raised to 23. This particular number, 6.022 times 10 raised to 23, is called as the Avogadro number, named after Amedeo Avogadro. This honor has been given to Avogadro because of his great influence in determining so many physical constants during the study of chemistry, and especially the physical chemistry aspect of chemistry. So when we talk about 1 mole, the mass of 1 mole of a substance is the molar mass of the compound, or the atomic mass of the element. We can see that the quantity looks large and different, but the mass represents 6.022 times 10 raised to 23 particles. So when we get the mass of 6.022 times 10 raised to 23, the units are grams per mole. However, when we get the mass of 1 molecule, then we designate the mass of 1 molecule as a molecular mass, and it is the mass in atomic mass units for 1 molecule. The atomic mass unit is actually a very small unit, and it is obtained as 1/12 the mass of 1 atom of a carbon atom, having the number of protons, 6 protons, and weighing exactly 12.00 gram per mole. Now, sometimes when we are calculating the molar mass of compounds, the sum of the compounds has water included in its formula. In that case, we have to add up these molar masses a bit slightly different. For example, aspirin C9H8O4 has the molar mass of 180.2 grams per mole. This particular aspirin contains 9 carbon atoms, 8 hydrogen atoms, and 4 oxygen atoms. So, knowing the atomic mass of each of the elements and the number of atoms of that particular element, we can multiply each of the elements by their atomic mass and the number, and then add up, and you get the total molar mass of the compound. Same thing for Fe2O3. In Fe2O3, which is basically rust, you see that you have 2 Fe and 3 oxygen. So 2 times the atomic mass of Fe plus 3 times the atomic mass of oxygen will give you the molar mass of that particular compound, Fe2O3. Now, when you look at calcium chloride dihydrate, the molar mass is calculated. First, the formula, how it is represented. CuCl2 dot 2H2O. Please note that the dot in between the two compounds indicate that it is a bond of hydration, and it tells you that there is a link between the water and the salt that is there. Such kind of salts are formed when we crystallize the compound out of water. This crystallization with water in its structure gives the compound a beautiful crystal structure as well as color. Now, in order to calculate the molecular mass of this, remember and note the dot does not represent a multiplication sign, nor does it represent a decimal. It tells us that you have to add the molar mass of copper chloride and then find the mass of 2H2O and then add them up together. So in copper chloride, you have 1 copper, 2 chlorine. So multiply the chlorine, 2 times the atomic mass of chlorine plus 1 time the atomic mass of copper. Add that and you get a 1 molar mass of copper chloride. On the other side, you can see that the water has a formula mass of 18.02. So multiply 2 times 18.02, you get the total mass of the water present. Then add up both the molar mass of the copper chloride and the molar mass of the water, and then you get the molar mass of the compound that you are talking about. Now, just a quick review. 1 mole is equal to the formula weight in grams, and it can be, the formula weight can contain atoms, molecules, or ions. Next, the conversion. How do we do mass to mole conversion or moles to mass conversion? So these are almost identical, but reverse opposite direction calculations. So if you have the moles, then multiplied by the molar mass of the compound and divided by 1 mole. If you have the grams, then multiplied by 1 mole and divided by the molar mass of the compound to get the number of moles. And you can see below how it is done. 16.5 grams of carbon times 1 mole of carbon, and you divide that by 12.01 grams of carbon. So you get the answer 1.37 moles of carbon. Now this example is a very good example to show you how to use dimensional analysis in calculating your results, and also how to use the conversion factor. Dimensional analysis means you must introduce your units in the problem when you're trying to solve. Conversion factor gives us the equivalence between 2 different units. In this case, 1 mole of carbon and 12.01 grams of carbon. And therefore, you can get the answer. Where are you is the question. At the beginning, you are in grams of carbon. Where do you want to go? To moles of carbon. Now, this is another example of how to do conversion from atoms, from grams to atoms. So how do we do? Very simple. Convert the grams of magnesium to mole of magnesium. How does one do that? You use the conversion factor 1 mole magnesium divided by 24.305 grams of magnesium. Cancel out the units, and then when you get the mole, you multiply it by 6.022 times 10 raised to 23 magnesium atoms present in 1 mole. And then you get your answer in so many atoms of magnesium. Again, the same type of formula and calculations. You want to find out the grams present, the grams of chromium. So now you're not asking for the grams of the whole entire compound, but you are asking the amount of chromium present in 25.1 gram of chromium acetate. The first step to do is to calculate the molar mass of chromium acetate. The formula is given, remembering that the subscript outside the parenthesis applies only to the elements inside the parenthesis. So when you expand this formula, you get 1 chromium, 6 carbon, 9 hydrogen, and 6 oxygen. Calculate the mass of 1 chromium, 6 carbon, 9 hydrogen, and 6 oxygen. And then add all of that up, and you'll get 229.13 grams per mole. From that, you convert the 25.1 grams of chromium to mole of chromium acetate. Once you get the mole of chromium acetate, you know that in the formula there is 1 chromium. So you multiply by 1 mole of chromium and divide it by 1 mole of chromium acetate. And the mass of 1 mole of chromium is 52 grams per mole. And then you calculate and solve the number. Next, we're going to do the percentage composition. Percentage composition of any element in a given formula is very easy to determine if you know the total mass of the compound as well as the amount of each element present in the compound. Because when we calculate the molar mass, we actually get the grams of each element in the compound. So atom of an element times its atomic weight divided by the formula weight of the compound. Whatever answer you get, you multiply by 100 and you get the percentage of that particular element. Now you can see this in the next 3 slides, how each percentage of each element is calculated. I'm just going to show you the first calculation because then you can calculate, check out the slide, the following 2 slides and make sure that you get 100% for the compound calcium hydroxide CaOH twice. Noting that there is 1 calcium, 2 oxygen, and 2 hydrogen in the compound that is there. The formula to be used is atoms of an element multiplied by the atomic mass of the element and divided by the formula weight. The answer you get, you multiply by 100. And so here, in this case, there is 1 calcium. The atomic mass of calcium is 40. The total mass of calcium hydroxide is 74.1. Because how do we get 74.1? Because oxygen is 16 and hydrogen is 1.01. So 16 plus 1.01 is 70. And so then the times 2 is 34. 40 plus 34 is 74. And So you get the number. And in that way, you can get the percentage of each of the elements that are there. Once you get the percentage of each element, make sure that it totals up to 100 or comes as close to 100 as possible. Now, this is the practice problems, so try to do it by yourself. And there are different styles of calculation, so that all what we have studied above is represented in the this particular question. So you have to go from grams to moles. So grams of sodium hydroxide divided by its molar mass will give you moles. Once you get the mole, you want the molecules. So multiply the mole by, in 1 mole, there is 6.022 times 10 raised to 23. So you'll get the molecules. And then there is a separate independent question given to find out how many moles of water are present in 4.2 times 10 raised to 25 molecules of water. Next, we come to empirical formula. There are 2 ways to do it. The first way is the simple way. You look at the formula that is given, and then we can write the empirical. How? Empirical formula, by definition, is the simplest formula of a compound. That means whatever the formula is given to you, see whether you can simplify that particular formula. That is, when I say simplify, it means the number of atoms. You check whether the number of atoms can be simplified or lowered down. And by how many units can you lower down? For example, we have C8H9, 18. Now, 8 and 18 is divisible by 2. And therefore, on simplification, the number of units is 2. And the empirical formula is C4H9. Because you divide 8 by 2, 18 by 2. And whatever divisor you use, that is the repeat units. So basically, we are trying to find out how many repeat units are there in a molecular formula. In order to calculate the molecular formula of a compound, given the empirical formula and the mass, what are the steps? In this case, you can see the simplest formula, First, let's look at the formula, the problem. The simplest carbohydrate is glyceraldehyde. Its empirical formula is CH2O. Its molar mass is 180.02. What is the molecular formula of this compound? First thing we have to do is calculate the empirical formula mass. So in the empirical formula, we see that we have 1 carbon, 2 hydrogen, and 1 oxygen. So 1 times 12.01 plus 2 times 1.008 plus 1 times 16 gives you a total of 30.026. Now you calculate the number of repeat units. How do you calculate that? The number of repeat units is actually calculated by dividing the molar mass given to you by its empirical formula mass. In this case, 180.02 is divided by 30.06 to give you an answer 5.998, which we can approximate it very close to 6. And therefore, we have 6 repeat units, and therefore the formula is C6H12O6. And this type of calculation is exactly reverse of what we did in the previous slide. Now, it asks you to find the empirical formula once the percentage of one element is known. And therefore, a general formula is given. If one of the percentages of one element is known, and if the compound contains only 2 elements, then it is possible to find the amount of oxygen. In this case, it is NXOY. So you will want to find out what is the ratio of X and Y, or what are the numbers equal to X and Y. So first thing we do is find, because nitrogen is 46.67, we have to find out what is the amount of oxygen. And in doing so, okay, that's the second part of the problem, because you have to identify it. But let me see. Yes, in doing that, how do we do it? We determine the percentage of oxygen. The total is 100%. So percentage of oxygen plus percentage of nitrogen must equal 100. So 100 take away 46.67 gives you 53.33. Next, you determine the moles of nitrogen. So 46.67 divided by 14.01 will give you 3.33. Determine the mole of oxygen in the same way. Percentage. Whenever we talk of percentage, remember in 100 grams. So in 100 grams of the compound, 53.33 grams of oxygen is present. So divided by 60 and you get 3.33. Since both the moles are the same, if you divide it, the ratio is 1:1. And so the formula is NO. Once you get the formula, you can go back and answer the multiple choice question, which of the possible compounds it is, because nitrogen has a tendency to form a large number of compounds with different states. Now, from now onwards, if I'm not, okay, in between all of these are different types of review application questions. Some of them I have solved and some in order to show you. Let me see, I think I've solved this question. If this is a review application, calculate the mass and convert to percentage to get molar oxygen. The problem is this, that ammonium perchlorate, NH4Cl O4, is a common fuel component of solid fuel rockets. If 75% of the oxygen in ammonium perchlorate was converted to molecular oxygen, how many grams of molecular oxygen would be produced from 117.5 kilograms of ammonium perchlorate? You're given the atomic masses of nitrogen, chlorine, oxygen, and hydrogen. And the answers, one of these is the answer. In order to find out which one, we solve it like this. First, first step is to determine the molar mass of ammonium perchlorate. So in ammonium perchlorate, there is 1 nitrogen, 4 hydrogen, 1 chlorine, 1 chlorine, and 4 oxygen. And so you multiply it, each of the elements by its atomic mass, and you get the total mass per grams per mole. Convert the kilograms given to grams. Then the next step is to convert the grams to the number of moles of perchlorate. Once you get the moles of perchlorate, then you convert the moles of perchlorate to the moles of molecular oxygen. How do we do that? Molecular oxygen as such is O, but we need O2. So what we do is, there are 4 oxygen atoms that are there. So you have 2 molecules of oxygen. So therefore, the moles of perchlorate 1000, you multiply it by 2 and you get 2000 moles of oxygen. Convert the moles of oxygen to grams of oxygen by multiplying it by 16. And then you determine 74% of that and you get the answer as 24,000 grams of molecular oxygen. And then you solve it. and compare the results on the top. Now, these are review questions. For a few slides, you will have some review questions, and then once you get to complete the review questions so that you know how to solve different types of questions that are there. Next, we come to the hydrates. We saw copper chloride, 2H2O. A hydrate is a substance composed of an inorganic salt and physically bound to water, and therefore Mx is the salts dot NH2O. N is the ratio of moles of water to 1 mole of salt, and that's how you calculate it. When you get, so a compound, a salt, when it contains water, we call it as a hydrate, and when it loses water, we call it as an anhydrate. And so when designating the names, we have to use the prefix mono, di, tri, etc. to represent how many water molecules are present. So we give the full name of the salt, put a prefix to indicate the number of water molecules, and then instead of writing water molecules, we write it as hydrate. So in the first case, you have barium dihydrate. Second case, sodium pentahydrate. When we heat a compound, especially a hydrate, on heating, it will lose its water of molecules. And for every mole of hydrate, it will lose N moles of water. And in this case, the N is 2. After heating, any mass that remains behind is due to the salt residue. And the salt residue is called as the anhydrate. Mass sample minus the mass of the residue will give you the mass of water lost. Once you know the mass of water lost, then we can calculate the formula of the compound, or the formula of the compound, or basically you're going to try to calculate the N value. So determine the formula of the hydrated salt based on the masses of water and the dehydrated salt. The mass of sample, you have your data must include mass of sample before heating and after heating, after which you will calculate the mass of water lost. Once you get the mass of water lost, then you can find out the moles of copper sulfate. In this case, of course, this is another formula that is there, copper sulfate and water molecule. It has a beautiful turquoise blue color. And when you heat it, the copper sulfate, dehydrated copper sulfate or anhydrate is colorless or ash white. And knowing the masses of both of these compounds, we can determine the mole ratio amount of water relative to the amount of copper sulfate. And this is the general step we use to calculate. So moles of water from the hydrate and moles of anhydrous salt. And after this, I think all the questions are self-study. So complete going through all the review questions so that you are able to calculate and understand each of the terms as well as the formula and know how to calculate the various problems that is associated with this. And again, remember that these problems do crop up again in different chapters because empirical formula and molecular formula has many applications, and you need to know how to find out the formula of the compound. And with that, I'm going to stop the share and end the meeting.